We begin in the Eagle Nebula, 7,000 light-years from Earth. A nebula is a large collection of interstellar dust that are the remains of a star that underwent a supernova millions of years ago. This dust, as it flows through interstellar space, can collect, acting as a nursery for new stars to be born. After enough of this gas collects, what is called a protoplanetary disk is formed, like Elias 2-27, which is 450 light-years from the Earth. It is in these protoplanetary disks that the gas can start to form the general shape and outline of a star system, which will later give birth to stars, planets, and asteroids. In the center of a protoplanetary disk will be a protostar. These protostars are large collections of gas molecules that are beginning to heat up and produce light. V1647 Orionis, which is 1,470.6 light-years from Earth, is a great example of one of these. Fusion does not yet occur in protostars, although, for most of them, it is just about to begin. If a protostar does not collect enough dust, it will unfortunately not become a full star, and instead a glorified gas giant, known as a brown dwarf, just like Gliese 229b, which is 18.8 light-years from the Earth. Now, these brown dwarfs, although not being stars, can still have many interesting properties. Did you know that on some brown dwarfs it can rain molten iron and sometimes other carbon-based materials like diamonds and coal? And now we go on to red dwarf stars, when a star is officially born. Red dwarf stars, like TRAPPIST-1, which you see on your screen now, are the most common stars in the universe. Red dwarf stars do undergo fusion, but it's very slow and typically involves hydrogen. Red dwarf stars last the longest because they burn their fuel the slowest. They are very small and don't have very much mass, usually around 20% of the mass of the Sun. A fun fact about TRAPPIST-1 is that it has 7 potential planets that could harbor life, although don't expect to be going there anytime soon. It's 39 light-years away, meaning our radio signals from 39 years ago are just now reaching there. And now, we move on to the most recognizable of the star's life cycle stages. What you see before you is not the Sun, rather Alpha Centauri A, the closest star to Earth, only 3.47 light-years away. That may seem small, but that means it would take Juno, the fastest moving man-made object, 14,000 years just to reach it. In yellow dwarf stars, fusion is quicker and can be done with heavier elements. Hydrogen is used to make helium, which can go on to produce carbon and sometimes even oxygen in yellow dwarf stars. These stars aren't as common as red dwarfs, but are still very common.
Next, we travel to Sirius, a perfect example of the next stage of a star's life cycle, the main sequence. Sirius lies 8.58 light-years from the Earth. A main sequence star is a star that's around the middle of its lifespan. Most stars in the universe are main sequence stars, around 90% of them. Now, in main sequence stars, for the most part, only carbon can be fused, but larger, higher mass main sequence stars can sometimes fuse things like neon. If the star is fusing any nuclei that are larger than these, it's most likely beyond the main sequence. Next, we find ourselves next to Arcturus, 36.66 light-years from Earth, and in the final stages of its life, the red giant, or in this case, supergiant stage. In a red giant, helium fuses into carbon, which fuses into neon, which fuses into silicon, and can even fuse to iron deep in the core of a star. At this point, almost all of the light elements are exhausted, and so the star begins to rapidly expand. This causes the star to become less spherical and bulge in some certain spots. This is why the star you see on your screen right now, Arcturus, is not very well held together. As time goes on, the star will continue to lose its gases and emit them, expanding more and more, until eventually it undergoes a huge reaction in its death. Depending on the mass of the star, this reaction can produce different things. When a medium-mass star dies and loses all of its lighter gases to space, what's left behind is a dense ball of carbon and oxygen, a white dwarf. Van Manen star, which is 14 light years from Earth, is a great example of one of these. It's a relatively cool and small piece of carbon and oxygen that floats through space and eventually loses its energy and becomes a black dwarf. However, this process can take trillions of years. No fusion occurs at the white dwarf stage of a star's life. We now find ourselves in a quite beautiful place, much like the one that we started in, the Cat's Eye Nebula, 3,000 light years from the Earth. This is what we call a planetary nebula. After a larger mass star dies, but doesn't have a core that becomes a neutron star or black hole, what's left behind is a nebula, with lots of gas clouds. These gas clouds are massive enough to form their own stars, and so, in a sense, a planetary nebula restarts the star's life cycle, with a white dwarf in the center. Next on the tour is the Crab Pulsar in the center of the Crab Nebula, 6,500 light years from Earth. A pulsar gets its name because it releases pulses or waves of electromagnetic radiation and spins extremely fast because of the momentum it got from the energy during its death. Pulsars are extremely dense and can almost be looked at as balls of pure neutrons from atoms smashed together. So dense, in fact, that 1 teaspoon of a pulsar weighs as much as a mountain. Either way, you do not want to get close to these things, as you'll die almost instantly from the extreme doses of radiation. 6,000 light years from the Earth is a very special type of star, a Cepheid variable. Although this isn't an entirely new star stage, Cepheid variables, like RS Puppis, are very important to plotting the Milky Way galaxy. These stars release regular waves of magnetic radiation, which we can detect with radio telescopes and determine their distance from the Earth. Using this method, we determine the size of the Milky Way galaxy with Cepheid variables. And in the center of the Milky Way galaxy, 8,000 parsecs away, is Sagittarius A, an example of the most intimate stage of a star's life cycle, a black hole. When an extremely massive star dies, its core collapses, forming a singularity, an infinitely small and infinitely dense point in space. The singularity is so dense and has gravity so strong that even light cannot escape it. The point at which light cannot escape it, or any matter for that matter, is called the event horizon. PSR B1509-58 is an example of a neutron star, 7,000 light years away from the Earth. A neutron star is much like a pulsar, but much tamer, much calmer. It is still extremely dense, and gets its name from basically being a densely packed ball of neutrons. The surface of a neutron star is comprised of a thin layer of plasma, about 10 centimeters. The deeper you go, the heavier elements you'll find, like iron. Sometimes you'll just find atomic nuclei slammed together extremely tightly, and then it will get to the point where all you can find are densely packed neutrons piled on top of each other. The cores of these neutron stars are actually extremely mysterious. We don't know what may be on the inside of these, maybe some quark-based superplasma. However, this is all due to speculation.